Hello and welcome to the ARM track part 2 for today, even though it wasn't announced that way, but we just happened to get scheduled right after each other, which is good. So you heard all about our current business plans for ARM half an hour ago, but let me still give you some introduction of what ARM really is, because you don't probably know what it is because you're sitting in here. So you all remember what ARM devices from your palms, right? Your phones, your tablets, your whatever, all of those are running ARM. And they're running ARM because they're really low power, but they're also not incredibly fast. They're fast enough, but they're not incredibly fast. But what ARM considered a couple of years ago is they realized ARM is going into servers because every time one of these small devices talks to any device out there, they need to talk to an x86 box these days, or usually the x86 box. And that's a huge market, right? And ARM wants to win huge markets, so they also started to conquer the server market. And we're actually right in that sphere right now. We're right in that battle with the first ARM server chips coming out, being available to market, and that's basically what this talk is about. Since I've forgotten the covering slide, this talk is going to be done by me, Alex Graf. I'm a software engineer at SUSE, Andy Walfer from ARM, and Dirk Miller, also from SUSE. What you see here is a very confusing chart. Let me quickly explain it. Depending on which chart you look at, everybody's trying to tweak it in a way to make it look like ARM is either good or bad. This chart basically just shows you spec int. That's the first thing to take a look at. Spec int just tells you how fast can a CPU add one-on-one, basically. It doesn't tell you how fast it can process your data. It doesn't tell you how fast it can burn through SQL statements. It's just adding one-on-one. And then to the top, the higher up the core goes, the faster a single core is. The further to the right you go, the faster the full chip is. What you actually care about at the end of the day is you want to be at the right end bar, right? That's for most workloads that scale well, that's the important factor. Current generation ARM chips are the three down here. So the AMD one is an ARM implementation. Xgene is from Applied Micro. Cavium has their own one. You can see that they don't have amazing single core performance. In fact, it's actually pretty bad compared to Intel systems, but still way faster than your phone. However, you're getting into regions where you end up in Xeon spheres with a full system on chip. The reason they're ending up there is you can probably do the math. One of those Thunder X systems has 48 cores. If you had 48 times okay fast, you end up with a pretty fast system. That basically led to the conclusion from the ARM side that, well, what workloads do we actually care about at the beginning for our ARM chips that, well, since they have a heritage in the mobile space, aren't incredibly fast? Well, it turns out there are a lot of use cases out there that don't need all that much CPU power. You don't need to add one-on-one a lot. You need to shove data from left to right really fast, yes. And you need to fetch data really fast to memory and push it to memory really fast, yes. But you don't really need to add another one to your equation. So all of those workloads listed up here are actually pretty well suited for an ARM server, since they don't need all that much CPU power. So based on that, we went ahead and created a list of what you can expect to see in the ARM space throughout the years. And throughout the years includes history. Has any one of you seen a storage server based on ARM? All right. So storage is a field where ARM is actually present in already. You all know your typical NAS box, but even in real servers, real storage servers, they're there. You can, for example, go to CineSpace and get your own dedicated ARM-based server for cloud storage, for example, or which is still based on 32-bit systems even. Or Western Digital, HGST now, has a really nice prototype where they put a full Ceph node into the hard disk itself. So your full, like your hard disk itself then becomes the Ceph node with only a single OSD attached to it. But even in more recent times, so this is one year, this is from this year, for example, HPE has a storage server called StoreVirtual, and the fact that it's running ARM is completely non-obvious and nobody actually cares. It just happens to have a 64-bit ARM's core server chip inside. But since you're only interfacing with it using traditional fiber channel interfaces, you don't bother, right? You're just using that server as an appliance, so ARM is penetrating the server market even though you don't even see it. Sometimes you do see it though. Have you seen that box? Did you go to the showcase? It's at the ARM booth, so you can actually see and touch it in real. That's an applied micro Mudan system, which is a box they created for the Ceph market. So it fits a good chunk of hard disk in there, it has SSDs, lots of memory, 8 CPUs to crunch through them, 10 gigabit interfaces to the out. It's an actual server made for storage, and it runs SUSE storage. But another company went one step further, and that's SoftIron. So SoftIron does the same thing based on an AMD chip right now. However, what they do is they ship with SES only, basically. So this system, if you buy one, it's an appliance, and you buy SUSE storage out of the box just from them. Which brings me to the awesome announcement. I don't know if you've seen it, SUSE Storage 4 is getting out on December 2nd and will be available for HC4. So if you're interested in building a storage solution and you want to see whether it performs well on ARM, go ahead, do it. It's right there in front of your feet. So storage is easy, right? For storage, you obviously need lots of I/O. You don't care too much about calculations. There's another workload that's similar, and that's simple web serving. Very simple general purpose computing and serving. So companies figured that a while back ago already. The HPE Moonshot is from 2014, I think, already. It's been a while. You can still buy it today. PayPal, for example, is even using that in production. It's a system where you can plug in up to 48 cartridges with applied micro systems, chips in there. But there are even systems that came out this year. For example, Gigabyte started to ramp up their ARM attribution. They got you a good chunk of servers. I didn't mention all of them. This is an applied micro server, for example. This is a Cavium-based server. Each one of those sleeves, how do you call those? The slats. Each one of those slats contain a dual SoC board, which basically means they have 96 cores. So you have 384 cores in a 2U chassis. Gets you at least some performance, even though the cores aren't incredibly fast. But at the fifth of the performance times 10 from the side, from the count, you're still faster than an Intel system. So we have those now, where what do you do from the software, right? I mean, you can buy a server. You can buy a server for a couple of months now already, from Gigabyte, for example, or from redistributors. But how do you, what would you run on there? Would you want to run Ubuntu? No, of course not. You want to run SUSE Linux Enterprise server. That's the next really big, cool, awesome milestone. And this is where we are today. So you've seen the announcements. Where do we come from? So SUSE has a really long history of innovation, and especially in the ARM and in the ARM sphere. So what we built on to develop the ARM story is Kiwi, the build service, and OpenQA. This cable is weird. We have been developing openSUSE for almost 5 years now, openSUSE on ARM, and dived into the 64-bit ARM space with openSUSE back in 2014, before any hardware was available at all. So we were the first distribution even building properly throughout on ARM. Using the build service because it just allows us to really quickly, really quickly develop a distribution faster than anybody else really can. We're using Kiwi to develop images for those distributions. And OpenQA, well, if you haven't seen OpenQA, OpenQA is a way for us to do continuous integration on the code base that we have. So using the build service, we can develop the distribution really fast. But using OpenQA, we can then verify that all the changes we do really fast don't break our flow, right? So just to give you an example of what it looks like, this is an actual live example of /12 SP2 booting, SP2 for ARM booting. on OpenQA. So it just goes through the installation, runs a couple of things, then logs into GNOME and runs commands and runs applications and verifies that everything still works correctly, even though we just changed half the distribution. This is how we verify every single product out there now, and how we do it on all the different distributions as well, or different architectures as well. So to get to a point where we can actually use, or where we have a viable ARM story, we obviously need to work with partners, right? We can't just go and bring out an ARM distribution that doesn't run on any hardware. So we created the ARM Partner Program a couple years ago, 2 I think, where we started to invite partners, silicon vendors, OEMs, others, to go and join us in the story, in the journey, to create a viable ARM solution for SLES. And the culmination of this obviously is the the release of SLES 12 SP2. We're the first. Woo! So there was awesome press coverage. I really like the picture. SLES 12 SP2 is available for ARM today. You can basically buy it from us if you want to license it for appliance deals or similar OEM deals. If you're interested in buying it, just go to Jay and tell him you want to buy it. It includes everything you would expect from a normal SLES distribution. The whole thing is there. I don't know what Jay covered in the talk beforehand. And it runs on these device types that you see down there. So it runs on AMD, on Applied, on Cavium, on NXP, and on Xilinx hardware. Make sense? Awesome. So this is all today's state, right? So we're still looking at today. One thing that's pretty new, or that will basically collide with the time frame when we release SLES, is that you're going to see ARM conquer, or not conquer, but enter the content delivery market. And that's very simple. I mean, if you look at those servers, each one of those has 2 40 gig ports and native built-in acceleration engines for SSL and compression, which is the perfect platform to shove data into the internet really fast. So that's why you're going to see content delivery as a big field that ARM is going to be, a big space that ARM is going to be in. Another one is going to be big data. And big data is also very simple for the reasoning. If you talk about big data, people talk about Hadoop and Spark. Hadoop is dying, Spark is basically the current generation, but everything there is running on Java, and Java is available for ARM right now. So that's the only thing that's keeping you from it is the single core performance, and we're going to see that increase throughout the next couple of years. So every vendor that we talk to basically promises about double the performance for the next generation. If they keep up that pace, we're going to probably surpass Intel really fast. Anybody got the pun? All right, good. But what's interesting is new fields that we're not really big in right now, or not that we don't conquer completely or penetrate completely yet. So the networking space, for example, is something that opens completely new platforms to us. If you look at the traditional networking space, this is a traditional networking system, right? This is an NXP Freescale system, and Freescale used to build their chips all around the power architecture. Now, if you look at their current systems, you saw their name earlier on, their new systems are actually built around ARM, which means that we now have SLES running on network infrastructure hardware that we weren't running on before. So you can actually have opportunities and possibilities that you couldn't imagine with a normal SLES beforehand. And the same goes for Cavium. So Cavium used to build everything around MIPS on the networking equipment chips, and now they're one of the big ARM players. So again, you can run SLES on there and do your amazing packet processing pipeline as an application on top of a stable OS that was not possible before, because the only chance you had was to grab some random Yocto distribution and maintain everything on your own, basically. In parallel to that, to the hardware vendors moving over to ARM, there's also another movement that's happening, and that's the NFV space. So with NFV, basically what those guys considered was, Well, we have these general purpose servers, right? Servers that can only crunch data and show stuff from left to right, maybe. But they don't really have special accelerators or aren't really fast in specific networking workloads because they're not built for it. And then you have these other traditional network equipment systems that are single purpose built. You build one system for one specific purpose. You have your 3G base station thing, and that's just it. And you shove a lot of accelerators in there. Now, with NFV, the idea is that you just basically combine those two ideas. You build something that's not completely general purpose, not completely special purpose. You have a bread in between, and you put virtual machines in there that then have access to accelerators in hardware that just get passed through. That's essentially the idea of NFV. And with that, SLAS comes into play again as well, because, well, if you're running on a reasonably general purpose server, why not run it on SLAS? What's really exciting is HPC. So remember what I started off with, that ARM isn't that fast? Why is HPC in that field, right? I mean, don't the HPC guys want to be like really fast, don't want to have like really fast CPUs? Well, it turns out a lot of places actually start developing for ARM right now to be equipped for the future. So you're seeing the Barcelona Supercomputing Center, for example, they're building up ARM servers right now. The Sandia National Labs have started to work on special engines that allow them to write their HPC applications towards an abstract language that translates into GPU, x86, ARM, whatever at the back end, just to be able to not get vendor locked in. Right? E4 has servers specially built right now to go into the HPC market. Penguin Computing has a special set of servers just for the HPC, or well, just for ARM. They're an HPC vendor. Cray has announced 2 years ago already that they want to work with Cavium to evaluate the ARM market. The Chinese are trying to build their next generation supercomputer around ARM. And that's yes. That's a really cool new chip. So if you look at that one, that's basically the Chinese entrance to ARM HPC chips, and that one already surpasses basically most of the chips that we have out there right now. So this is going to be a very, very interesting move. But I mentioned that the ARM guys, or those people are really just preparing for the future, right? So what is that future? Well, the future is actual HPC deployments, right? So right now they're just toying, they're translating their code, they're making sure that it runs on ARM for a future where ARM is actually a viable option in the HPC space. And it's going to be viable also because of a couple of different reasons. The first reason is obviously because the chips get faster. But there's more. ARM is currently investing a lot into being competitive in that field. So C6, for example, is ARM's answer to NVLink, if you've heard of that one. NVLink is a way to combine a power chip with an NVIDIA GPU. It's a cache coherent PCI bus, basically. The other big reason is exascale. So every single continent, basically, continent, topological, I don't know how you want to call it, everybody has their own exascale initiative. So there's an exascale initiative in Europe. There was the Barcelona Supercomputer Center that you saw. There's an exascale initiative in the US. That's Fast Forward. So Fast Forward is part of the exascale initiative. And then there's one in China and in Japan. So Cray, for example, put into that exascale initiative a proposal to base on ARM, and you see the numbers there, 2020, 2022. That's when you're going to see actual HPC deployments in the US based on ARM chips. I mentioned Japan. You saw the Fujitsu announcement? So Fujitsu announced that they currently have their top generation supercomputer in Japan, is built around a Spark chip, and they're moving to ARM. So that chip that system is going to be all ARM-based, and they're basically going to take what they have, all the knowledge they have, and integrate it into the ARM ecosystem. Basically, make half of that available to everybody else. Then even, right? So they take all their history and their experience and donate it to other ARM vendors, so that people who are not Fujitsu can still benefit from it. And use an ARM server, or not one, a lot of ARM servers in their next generation supercomputer. One of those pieces that they put in there as an experience field is the scalable vector extensions. It's similar to AVX, just that it is bit width independent. So the instructions don't care whether your CPU implements 128-bit registers or 2 kilobyte registers. It still works the same from a code flow. So you can write your HPC program against a cheap device, similar to the Raspberry idea, right? You can write your HPC program against a simple ARM server and then run it on a really big ARM server that has really big register sizes and is really expensive. And it's going to run that much faster on the big system. So Fujitsu is really excited about the whole thing. They were the only ones really vocal about it yet. But essentially every continent is looking at that direction of going into HPC with ARM. So this is going to be a very, very exciting play. Obviously, it's still in the future. So if it is going to materialize, we can't predict. But it looks pretty promising right now. What you will also see is by 2018, 2019, you will have chips that probably will be fast enough and reliable, well, have RAS features that make them reliable and robust enough that you want to trust your traditional databases with them. And maybe by that time, hopefully, people will also port traditional workloads like databases to ARM. It's the hope, prediction, right? And even further down the line, you will then see ISVs pick it up and everything. So everything that's in there beforehand is open source. It's just normal slash space, people that can port their own code to ARM, that don't have to rely on the ecosystem. By that time, it will be a completely normal, viable option to x86 if things go according to world domination plans. So where is ARM today? Today, ARM has a really good ecosystem of CPU vendors that implement the ARM architecture. That's really one of the strong points. It's similar to an Android versus iPhone comparison, right? With an iPhone, you can only buy it from a single vendor. With Android, you can buy it from a couple hundred. And the same goes with ARM. So on x86, you can basically just buy it from Intel and AMD. On ARM, you can buy server chips from all of these guys, and the number is only going to increase. Well, hopefully. Also, even today, if you want to start working on ARM, you have a reasonably good choice of systems that you can choose from. You can buy something today. You can roll into that space. Is it going to roll your dice properly? You have to evaluate it. Is it going to be more power saving than your x86 system? Probably not. But it makes you, if you look at it today, it basically gets you prepared for what's to come tomorrow. To get to that point where everything does work, ARM invests a lot into making the ecosystem work, so all the open source projects get ported. We are doing a lot of our share for it as well. Basically, you have a viable option portfolio on ARM. There's a very slim chance that an open source project does not work with ARM today. So if you want to just see if it works, just give it a try. There's a good chance it does work. Just as an example, in the Linux kernel, Linux, which is the open source non-profit organization from ARM, is the third biggest contributor, third biggest commercial, well, it's not a commercial, third biggest identifiable. Linux and ARM together are the third biggest identifiable, non-profit, whatever. They're the third biggest, basically. Entity, identifiable entity in the Linux kernel development in 2016, which is where we used to be. So it's pretty cool. But where's it going? That's the important part, right? I mean, we're here already. Today is today, but where's tomorrow? So TSMC assumes that the whole data center story with ARM is what's going to drive 7 nanometers, which is the next big step on shrinking the process. So they don't assume that it's mobile phones. They assume it's the data center, which basically means they put a lot of faith into seeing the data center actually grow in the ARM space. You will see lots of new chip revisions. So Cavium has Thunder X1 out there right now. There will be Thunder X2. Applied Micro has XGene 1 and 2 out there right now. There will be XGene 3, which, again, both of these promise twice the performance of the previous ones. You have new people entering the market that you cannot buy stuff from today. Mellanox, for example, integrates their InfiniBand controllers, the next generation InfiniBand controllers, with ARM chips, ARM cores, into their own SoC. So you can then buy an SoC, a single SoC that already gives you native InfiniBand performance and capabilities. Qualcomm has officially announced that they are joining the server space, server game as well. And those were just the ones that I could find public references to, so I just made sure I start up Google and don't use any NDA information. So these are the ones that are basically public. You can definitely expect that there's more. So as I mentioned, the really, really nice thing about ARM is that you have the choice of your SoC vendor. And we're striving really hard from a SUSE point of view to make sure that we leverage that ecosystem. So that if you want to use a specific ARM chip, that we have it enabled. If we don't, let us know, and if it's a viable option in the server space, we can still talk. Which is why we have so many partners. So we're not only partnering with our silicon vendors, we're also partnering with a lot of OEMs and ODMs and whoever, even software people, to make sure that we have a working SLAS for you guys when you want to use it. So one more thing. I told you, right, there's this really big server that runs our SLAS code, and you would usually imagine that that has a specific system optimized for exactly it. And that's true. SLAS is optimized for really big systems. But the exact same software runs just as fine on the Raspberry Pi. You saw the announcement this morning. So the one more thing slide is moot. But we do have SLAS 12 available for the Raspberry Pi now. And it's running the exact same code base as you would run on a real big server. Same kernel, same user land, same everything. So anything you prototype on a Raspberry Pi runs the same on a really big server. So if you then run just a lot faster, yes. So if you then go and take that workload onto, say, your 96 core system, it will just work and it looks the same and it feels the same and it runs the same. Basically, the takeaway from this whole talk is most people ask me, why should I use ARM? Give me an incentive. Why should I be doing ARM? And you should basically walk away with the sentiment that you should wonder yourself, why should I not do ARM? Right? People are doing it. It's out there. Servers are in production. We are in a journey that is at the right spot in time right now, and is accelerating every day. The ecosystem is expanding from day to day, and we're in the game. You might be in the game too soon. Join the fun. Hooray! That was fast. Any questions? Blank faces, awesome.
I think it's one of the side effects of being so cutting edge or so new.
It's definitely a side effect of being new. Yes, well.
So the Raspberry Pi, we talked a little bit about that. So what did you have to do that was kind of different to the Raspberry Pi as opposed to the big servers.
What's different from the Raspberry Pi than the servers? Okay. There are a few things that make a small development board different from a real big blown up server, right? One thing is obviously the philosophy. So usually in the server sphere, server vendors have a really big incentive to work with enterprise distributions. For small development boards, they just sell the boards. They don't calculate in that they need so and so many dollars to pay for developers to upstream code and to maintain code and to support us. So basically for the Raspberry, we're on our own on a lot of things. Most of the upstream support that we are leveraging does not come from the Raspberry Pi Foundation. It comes from random upstream people, most notably a guy who works for NVIDIA, which is another company that also does ARM chips. That's really a really big hurdle since the big up servers, we can just always call someone and have them help us. The next big thing is because it's trying to be cheap, it's leaving away a lot of things, right? It's cutting off on costs as much as makes sense for a small board. So you don't have a real-time clock, for example. The system always boots in 1970. Well, that means you somehow need to have network connectivity to figure out what time it is right now. You just can't ask the board. It comes with its own way of doing firmware and everything. Very different from the usual workflow that we would expect on a server. And so we went ahead and actually modified that boot flow into booting similar to how x86 and normal ARM servers boot. So if you have a Raspberry Pi, if you got one this morning, or if you take the Raspberry Pi image, you will see that you have grub booting up. Well, the reason you have grub booting up is that you're actually booting an EFI-enabled U-boot on top of a Raspberry Pi firmware. So before you even get to the kernel, you already have 3 layers that are not existing in that normal Raspberry Pi image that you would get from the Raspberry Pi Foundation. It's another hurdle. There's basically that chip is designed for a 32-bit world, right? So we had to even enhance the kernel to be able to do DMA on those systems. It's small, it only has 800 megabytes of RAM, so we realized that conserving memory is really important. There were a good chunk of problems we had while developing it for that platform, but every one of those is very valuable because every one of those gets us into things that we wouldn't have been able to do otherwise. So for example, the booting flow is also the enabler to be able to run on NXP and Xilinx hardware because they also use a similar boot flow to what the Raspberry Pi does. Without them, we could just, I don't know, we couldn't boot on them basically. It would be a shame. The memory constraints were really important for us to realize that the same problem arises in virtual machines, right? So you want to be able to run a lot of virtual machines on a system. So if you're wasting memory, you can run less virtual machines. So having less memory consumption is actually a good thing even for big servers. It's helped us a lot in enhancing SLES in general, even though you wouldn't assume so if you look at the board. Mike?
So I got a question for you. Historically speaking, if you look at Intel versus AMD, it's pretty easy to choose between one vendor versus another. Looking at the large number of people involved in the ARM space, how are people making those decisions these days? What are the main factors where each vendor is making themselves unique in that space?
Always compare it to Android. Is basically my answer to that one. It's very simple. If you look at the Android space, I would say around 80% of people don't really look at why they're buying a phone. They just have a different view of the world. They don't buy it because they want to have 8 gigabytes of RAM. They buy it because the TV ad was really nice, right? You still have all those experts that go for details and want to make sure that they get an open source Android version on there, whatever. But most of them really just care about completely different factors, and it's going to be the same there.
And there's an element where traditionally in the x86 space you're having to make all software work on hardware that you can get off. Doesn't necessarily mean that it's the right fit for your workload. It's just what's available. Whereas with a lot of the ARM partners, you're able to actually, you know how your software works, you know where the bottlenecks are, you know whether you need fast interconnects, you know, whatever. You can actually pick and choose the right hardware to fit your software work. You can better match your requirements from software into the hardware space.
Are the vendors then marketing that way? I mean, this is designed for the storage space versus...
So some of them are. So for instance, Cavium have, as Alex mentioned, you know, for instance, with the CDN space, you know, they've got integrated SSL acceleration for decrypt, encrypt. They've got network offload built into the chip. Whereas in the x86 space, these are all add-on cards that up your cost, increase complexity, additional points of failure, etc. So some do market that way.
Does it answer your question?
Actually, what I've seen in our acquisition is we don't really carry manufacturers much yet. It's the vendor that holds the machine together to get requirements. So I think you're going too deep to dive. We don't say we want this chip. We go to HP or Applied Micro or something like that and say we need a box that does this. They deliver us to meet our requirements, and we really don't care which chip we use. They just tell us ARM, blah, 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 and we're like, we do what we want. That's the way we've done it so far. So, I mean,
Yep.
sorry for not securing. As long as it does what it's supposed to, that's what we're looking for in our application.
Yeah, but I mean, it gives the likes of HP or whoever that ability to go, okay, customer requirement is X, we can match those pieces that give us a budget to work within, and that's how it comes out.
To give you an example, Intel's business model for the E7s, for example, is heavily built around the fact that they assume that higher-end systems, for higher-end systems, they can charge like 5 times the amount of money. And high-end systems is basically defined by the number of memory channels and the number of interconnects they can have between different CPUs. Now, for an ARM vendor, that whole equation doesn't even exist, right? They don't care. If they just want to build a system that has 60 memory channels, like what the Phytium guys did, they just do it. And they suddenly are have 2 times the memory bandwidth that even the highest end Intel chip has, but they can sell it at half the price if they wanted to. So you will see combinations of things that completely fall out of the current way of thinking of what you would do with an Intel system. And that's essentially the danger for established systems.
Another area is vendor lock. So currently, a lot of companies are having to diverge and ensure that they don't have a single vendor lock in their chain on whichever component. It's a little bit tricky in the x86 space, but on ARM, your workflow can run on 8, 15, 20 plus vendors. So you've got much fatter pipeline from the supply chain to prevent any potential issues, price hikes, etc.
So
is built for purpose hardware. Doesn't this impact the way the operating system or the environment is built? So when you have a modular approach, you put parts and pieces together, you have the respective device drivers, you get a system on a chip, and so what would that be happening?
So there are multiple different aspects to it, but basically from a ground level, imagine it similar to the Raspberry Pi versus really big server story, right? Those were two chips built for completely different market segments. The big server was built for server markets, and the Raspberry was built as a TV setup box. That was basically what the chip was designed for. Yet slash runs on both of them, and the only major thing we had to do in the kernel was, well, have generic support for DMA and cable devices, but the big one was just drivers. And drivers is something we have on x86 all the time anyways. I mean, there's no difference to it. So ARM is doing a really good job at making sure that your normal code, your normal environment, your normal system level stuff is completely compatible throughout the whole chain. So even though somebody builds a special purpose chip, that one might just be slower in one area, or you might need a special accelerator driver for something, but it won't break everything completely, so you have to build your operating system differently. There's another movement coming in right now, which is very good, and that's that people want to move very function-specific piece of hardware into user space. So traditionally, if you wanted to use a crypto accelerator card, the only option you had was you write a kernel driver, because the kernel is the interface to hardware. And what we see now is that a lot of that gets moved into user space with hardware capabilities that allow you to isolate hardware and make it available to user space in a safe manner, so that you don't really have to do anything in / for specific purpose-built hardware. You can even go as far as implementing your own hardware in an FPGA and have the driver all in user space and run a stock / on your FPGA ARM chips. Just works. Make sense? All right. Cool. Well then, thanks a lot.